Swayam Prabha. Digital India. Educated India.
There is a plane of symmetry passing through the center of the cup, bisecting the cup handle and coming on the other side of the cup. Is it chiral now? There is no heart on the other side. There is only one side, there is heart. Chiral. So why can't we wear the left hand glove on the right hand? Because of the nature of the handedness of the glove. Similarly, shoes are also very specific for a particular foot. Because these objects are handedness, they are chiral in nature. Chirality in nature is plentiful. Here is an example of a flower which, by virtue of having the twist in the right hand direction, this is chiral. If you put a mirror image, if you put a mirror here and reflect the mirror image, the twirling will be in the opposite direction, right? So it is a chiral molecule, chiral object. I am always curious about whether an object is chiral or not. Whenever I observe something, I ask this question, is it chiral or not? Thereby you can practice your chirality. Now, the symmetry of scallop shells makes it achiral in nature. Chirality and achirality are opposite of each other. Why is this achiral? It has a plane of symmetry. The plane of symmetry is passing through the center of the scallop shell, right? On the other hand, if you take the snail shell, this has a twist in the right hand direction, it has a twist. And the mirror image is not exactly the mirror image, it's not the same shell. It's difficult to get the other shell with the other configuration in nature. For every 2000 of this shell, only one of this shell is formed. So this has the anti-clockwise direction rotation of the twist of the shell. So it is chiral in nature, right? Convinced? Similarly, we have Alamburi Shangu and Edamburi Shangu. These are chiral objects in nature. Again, Alamburi Shangu is far more available than the Edamburi Shangu. I don't know the reason why it is so, but for every few thousand of the Alamburi Shangu, only one of the Edamburi Shangu is formed. So Edamburi Shangus are very rare in nature. I don't know how many of you observed the millipede curling up like this. In the campus, there is plenty of millipede. You can experiment with them. Don't touch them. I don't know whether they are toxic or not. But they curl up in the anti-clockwise direction in this way. They never curl up the other way around. This is twirling of the hurricane. This has something to do with Earth's rotation, right? You have the twirling of the clouds of the hurricane, and that makes it a chiral object. How about a simple climber? This is a plant. It uses these structures to climb up the trees or bushes. This has a helical structure, right? helical structure. And what is the helicity? Is it a right hand helicity or left hand helicity? Left handed helicity. If you observe from the top of the helical structure, you go in this direction. So this is a left hand helicity of the structure, right? Spiraling of aloe vera, for example. Where is the spiraling of aloe vera here? Right hand helicity is what is present in the aloe vera. Quartz is nothing but silicon dioxide. Pure silicon dioxide is quartz. However, the way the structure is arranged in the solid state makes it a chiral molecule, chiral object. Natural quartz crystals are chiral in nature because of the kind of arrangement that the solid state structure has in the system. And that is why they are chiral in nature. This is one of the earliest examples of chiral objects in the world, because even before chemistry was developed, the optical rotation was observed and chirality of objects were recognized at that time. This is a black bug. This is available in IIT Madras campus. I don't know how many of you have observed this black bug. If you observe carefully the horns of the black bug, this is twisted in one direction and this is twisted exactly in the opposite direction. There is a mirror symmetry placed on the head of the black bug, which is a reflection of the right hand and the left hand helical structures of the horns. This is called the big horn. Big horns are having mirror image relationship, twist of the horns of the sheep here, right? How about curly hair? Curly hair is an example of a helical structure, and you have only one kind of helical structure, curly hair, natural curly hair I am talking about, not the permed one in the beauty salon. Natural curly hair is only one type of available because of the alpha helical structure of the proteins that are associated with the curl. Chirality in divinity. Ardhanarishwarar. Ardhanarishwarar is half woman and half man, right? So this is a chiral object as far as the chemistry is concerned, for example. How about Vinayaka? We have both left hand side, right hand side Vinayakas with the Tudikai on the left and Tudikai on the right hand side of the structure. The cosmic dance posture of Nataraja itself is a chiral. There is an old movie in which N.S. Krishnan is a comedian. I don't know how many of you know N.S. Krishnan. I am talking about comedians of 1960s and 50s. And he suddenly gets doubt whether the Nataraja is dancing with the left hand up, left leg up or right leg up. Here it is alternating between the left and right of the. When you go to Europe, some point of time in your career you would go to Europe and other countries and go and visit the churches which are very nicely decorated interior. And the churches have columns which are chiral in nature. Helical structures are very common in the columns of the churches. I have observed this in several of the churches and I have taken pictures of the churches. These pictures are not mine, but I have got an album of pictures of churches, in interior of the churches with helical structures like this. Man-made objects, if you look at, until now we saw only natural helical objects and structures. Man-made objects like a fan rotating in one direction, for example. It's capable of blowing air only in one direction, right? Because of the twist of the blade is in particular direction, it will push the air only in one direction and not the other way around. If you reverse the rotation of the fan, then it will blow the air in the other direction, right? These are examples of chiral objects which are synthetic in nature. Here is a natural inspired double helical staircase, for example. The staircase is double helical in nature. You can see that, right? Even the necktie is a chiral object. The necktie across the Atlantic is different from Europe. The English regimental stripe is having stripes in this direction, whereas the American regimental stripe is having exactly the mirror image relationship of the English tie. So even an object like tie, for example, can be chiral in nature. Now let us come to the chemistry aspect of chirality. Here is a chiral molecule, it is alpha amino acid. Alpha amino acids are building blocks of proteins, right? And they are chiral in nature. A carbon bearing 4 different substituent is known to be chiral. Why? Fundamentally, it doesn't have a plane of symmetry or axis of symmetry. It doesn't have any symmetry element present in the carbon. The carbon is a chiral carbon, asymmetric carbon. As a result of that, it is chiral in nature. Molecules with chirality, for example, these two molecules are mirror images of each other and they are non-superimposable. So they are chiral in nature. What is the view of the molecule here? If you look at the molecule from the bottom along the CH axis, this is how you will see the molecule. Can you visualize the molecule like that? You stand here and observe the molecule through the CH bond. Then the fluorine will be on the top, bromine will be on the left hand side, chlorine will be on the right hand side. This is exactly the mirror image of the molecule. So it will be fluorine on the top, bromine on the left hand side, chlorine on the right hand side. These are called the enantiomers. Enantiomers are optical isomers which have mirror image relationship, which is non-superimposable mirror image relationship. Now, S-limonene is a terpene that is available in lemon. Particularly the lemon skin has the oily substance which is limonene, and this has a lemon smell. Enantiomers are optical isomers which are mirror images of each other and non-superimposable mirror images. The plus limonene and R limonene differ in what way? Structurally, how is it different? What is different about them? This is behind the plane of the board. This is above the plane of the board. So the configuration of this carbon alone is different. Rest of the molecule are same. Right? Only the configuration of molecule at this particular carbon is different. This is R limonene, this is S limonene. This nomenclature will come to it a little later. But look at the effect of the stereochemistry of the two isomers. One is having lemon smell and the other one is having orange smell. Our nose is very, very sensitive, right? It can distinguish between the lemon smell and orange smell. That is because the smell sensors in the nose are chiral in nature. So they are made of protein molecules probably, and they are capable of distinguishing between the two types of isomers from the point of view of smell. This molecule is known as carvone. Carvone is also differs only in one carbon, the chirality of the, this is the chiral center of the molecule, and this is above the plane of the board, and this is below the plane of the board, and that is the only difference between the two isomers of carvone. However, carvone smell, the R isomer has spearmint smell. This is a bubblegum smell, for example. Spearmint is an active ingredient in the bubblegum. This is a caraway seed odor. This is a particular, something like perenjiragam. Smell of perenjiragam, for example. Jeera is what the Hindi word is for there. Artificial sweeteners, for example, are chiral in nature. They are made up of amino acids, amides. This amide bond is chiral in nature because of the center here is a chiral center. The center here is also a chiral center. The artificial sweetener, if we change the configuration here and here, it becomes a bitter substance. It is no longer a sweet substance. So with the proper configuration, you have to synthesize the molecule in order to market it as a sweetener. Otherwise, it will be a bitter. Biologically active chiral compounds have possible mode of action like this. Only one enantiomer is active, the other enantiomer is completely inactive. This is okay if it is a drug molecule, if you are taking a mixture of enantiomers. Only one of them is active towards a particular disease, the other one is totally inactive. You are allowed to take the racemic mixture because one is not going to do any harm, the other one is going to cure the disease. Both enantiomers have similar and equal activity. This is the ideal condition. 100% of the molecules can be utilized for therapeutic application, right? Because both the enantiomers are having a similar and equal activity. Both enantiomers are active, but their potencies are different. One is highly potent, other one is not so. In this case also it is okay to take a mixture of isomers because potential is there to use it as an active ingredient. Only thing is the amount of substance that is taken is going to be different because of different potencies of the molecule. Both the enantiomers are active, but the type of activity is different. This is dangerous because if you are trying to take a medicine for a headache and that starts to cause a stomach ache, for example, then it will be a problem. The activities are different. One enantiomer is useful, the other one can be highly toxic in nature. Such an example is the thalidomide case. Thalidomide disaster is due to the wrong chirality of the molecule. The R isomer is a sleep inducing, morning sickness curing drug. Pregnant women have morning sickness, right? And they take this medicine, they took this medicine in order to cure the morning sickness so that they don't feel nauseated. But the drug was administered as a racemic mixture. It's a plus isomer, or the R isomer and the S isomer are mirror images of each other. They took an enantiomeric mixture which is called a racemic mixture. And as a result of that, children with the deformation are formed during the pregnancy. This was a disaster during the 1960s, late 50s and 60s. Ibuprofen, for example, is a simple molecule, but it has a chiral center in it, and the S isomer alone is useful in nature. S enantiomer is an anti-inflammatory drug. Ibuprofen we know, right? L-dopa, in other words, the methyl dopa is a drug that is used for Parkinson's disease. It is an anti-hypertensive also, blood pressure reducing drug. S enantiomer is the only active enantiomer. So if you are taking both the enantiomers here, 50% of the molecule is going to be inactive and it's going to be waste of loading up the system. So in order to control the usage of the racemic mixtures versus pure enantiomers, the FDA, Food and Drug Administration of United States, have come up with guidelines as to how to use a racemic mixture in order to use it as a drug. Whether you can use it as a mixture or one has to purify it rigorously and get the enantiomers separated and administer the separated enantiomers or not is a question that was raised. As of today, if we are using a chiral molecule, we are supposed to demonstrate the potency of both the molecules, the toxicity of both the molecules, and the efficacy of both the molecules. Then only you will be allowed to sell it as a racemic mixture. Otherwise, you have to purify it and sell it only as a enantiomerically pure form. Thalidomide, I just now discussed, is anti-nausea, R isomer. S isomer has a prenatal deformities, which is teratogen. Limonene also we saw in a few minutes back. Aspartame sweetener is a compound which is this. The antipode is bitter in nature. Deveron and Navard are the analgesic antitussive. Antitussive is cough reducing medicine. You have the kitch feeling is there now, the cough, that is reduced antitussive agent like this, for example. Penicillamine, an arthritic substance. The R enantiomer is active, S enantiomer is toxic in nature. Insect pheromones are chiral in nature. What are pheromones? Pheromones are chemical substances secreted by insects for their communication purposes, mostly for communication purposes. Imagine a housefly is sitting in this corner of the room, and it's a male sitting on this corner of the room and searching for a female. The female is sitting somewhere in the room. How much effort it will put in to identify the presence of the female, considering the size of the housefly and the size of the room, for example. Therefore, the insects secrete this kind of molecules which are volatile molecules. These are esters or ethers kind of molecule. Esters and ethers are the most volatile material in organic chemistry. So, the esters are secreted, and from the secretion they can sense the presence of the female counterpart, this particular. So, insect pheromones are chiral in nature, and they are used as a communication device, for example. Insect pheromones are also used in controlling pests in the fields, right? Because it attracts the opponent. The opponents are trapped in a trap, and thereby the pest control is taken care of in agriculture, for example. Their pheromones are used as pest control molecules. Salbutamol, I don't know if any of you are using the inhaler because of asthmatic problems, but the active ingredient in the inhaler is this molecule. Salbutamol is the molecule that is used in the inhaler, and this is because of the chiral center here. This can exist in the enantiomeric form. If you put a mirror image here, it will be a reflection of the opposite kind in this particular case. Cetirizine is an antihistamine. Many of you take antihistamine when you have allergies, and that has a chiral center here, and it's an optically active compound. Levocetirizine is an enantiopure drug that is marketed. So this molecule is not sold in the isolated, in the pure form. One particular enantiomer is isolated, and that is essentially used as a drug in this. This is another drug molecule which is antidepressant. How do we identify chiral molecule? Chiral molecules have the ability to have left-handedness and right-handedness. Therefore, they rotate the plane of plane polarized light in opposite direction. The phenomenon is called optical rotation. Why there is optical rotation when a chiral molecule is placed in the presence of a plane polarized light? Plane polarized lights consists of what? Left circularly polarized light and right circularly polarized light, right? It's a composite of left circularly polarized light, right circularly polarized light. When the chiral object is placed in the beam of the plane polarized light, the velocity with which it travels, the left-handedness travels, is different from the right-handedness. So, because of that, the optical rotation phenomena is observed. Plane polarized light is this is one particular plane, right? This is a magnetic component of the plane polarized light, and this is a electric component of the plane polarized light. Let us say perpendicular plane, it is there. If it is confined to only one plane, then it is called plane polarized light. If it is not confined to one plane, if it is propagating in all the directions, then it is non-plane polarized light. The way it is represented, the electromagnetic radiation is represented on a textbook plane of the paper, is always represents a plane polarized light. The optical rotation is such that if one enantiomer rotates the plane polarized light in the right-handed direction, then the other enantiomer will rotate it in the opposite direction in equal amount. Optical rotation for the plus isomer is plus 50, for example. The minus isomer, it will be exactly minus 50. So they will be equal amount but in opposite direction. A 1:1 mixture of enantiomer is called a racemic mixture, and it's not optically active. Why? They cancel optical rotation of each other. Molecule with one chiral center exists in two enantiomeric form. That is the R form and the S form, or the plus form or the minus form. Dextrorotatory and levorotatory forms. D form and the L form. The D form is the plus form and the L form is the minus form, provided the D and L are written in small letters, not in capital letters. Capital letter means entirely different phenomena. The small d and small l represent dextrorotatory and levorotatory. Dextro means right-handedness, levo means left-handedness. So this is a optical rotation that one can observe. How about molecule with more than one chiral center? If there are n number of chiral centers, then you will have 2 to the power n number of isomers, because for each chiral center you will have 2 isomers. So 2 to the power n number of isomers will be there. This is I'll write a realistic molecule not with X, Y, Z, but with chemistry. This molecule, if you write to, this is a common formula for a chemical substance. And if you write it in the stereochemistry manner, this is a Fisher projection formula. Now, how many chiral centers are there in this molecule? 2 chiral centers. What are they? So, how many isomers are possible? 4 isomers are possible. Can you write the 4 isomers? This is one of them. When I say isomer, I mean stereoisomer, not the other possible positional isomers and so on. Stereoisomer means it will have the same connectivity pattern. Connectivity will not change. Only the position of the groups are interchanged. Is this correct? So there are 4 isomers possible for this. What is the relationship between isomer 1 and 2? Enantiomers, because there is a mirror plane right in the middle of the 2 structures, so they are enantiomers of each other. What about 1 and 3? Diastereoisomers. What are diastereoisomers? Diastereoisomers are stereoisomers which are neither mirror image nor superimposable on top of each other. Constitutionally dissymmetric chiral molecule means what? Constitutionally dissymmetric means there are 2 chiral centers and both the chiral centers have entirely different groups, as opposed to constitutionally symmetric chiral molecules. Here, this is a chiral center. Constitutionally, it is ABC. This is also ABC. So, this is a constitutionally symmetric molecule, right? Sorry? The 2 chiral centers are bearing the groups, right? This is a chiral center having XYZ group. This is the chiral center having ABC group. So, they are not identical groups. Whereas in this case, this chiral center has ABC group, this also has ABC group. So, it is constitutionally symmetrical. Real life example of constitutionally symmetrical isomers are erythros and threos. These are sugar molecules which has two chiral centers, and the two chiral centers are constitutionally constitutionally unsymmetric in nature because of the CH2 and CHO. Tartaric acid, which is available from the red wine, for example. Tartaric acid has constitutionally symmetric groups HOH and COOH group. Here also HOH and COOH group. What is molecular asymmetry? If a molecule does not possess any symmetry elements, what are the symmetry elements? Axis of symmetry, plane of symmetry, rotational symmetry is axis of symmetry or plane of symmetry. It doesn't have a center of symmetry or a plane of symmetry. Center of symmetry. Then it is called a disymmetric in nature. Disymmetry means there is no symmetry element involved in the molecule. Such an example is this molecule with 4 different substituents which are not equivalent. So this is a disymmetric molecule. Chiral molecule need not be asymmetric in nature. Why? Only plane of symmetry need not be there. Axis of symmetry can be here and center of symmetry can be there. It can have a rotational symmetry. That is, axis of rotation can be there, but the plane of symmetry should be absent. This is a chiral pool of which asymmetric molecules are only a part of the chiral pool. There are plenty of chiral molecules which are not asymmetric in nature. This is an example of a chiral molecule but not asymmetric in nature. How do you visualize this molecule? What is the kind of visualization do you have? Consider this to be a cup kind of a molecule with the hydrogen pointing the backside. Otherwise, it is a cup with the hydrogen pointing outside. Why is this chiral? Because the mirror images are not superimposable. If we try to put this on the other side, this double bond will come here. It has a C3 axis of symmetry. Can you see that? C3 rotation axis is there in the molecule. The C3 rotation is essentially the CH bond axis of rotation. Let us say, for example, something like this is a representation of the molecule. There has a C3 axis of rotation. Yeah. Yeah. You wanted to ask something? This part? What is the question? Okay. This lecture notes will be available to you at some point of time. So you don't have to copy down in a hurry. Can I proceed? So this is a threefold axis of symmetry molecule, but it is a chiral molecule. So it is not a disymmetric molecule, but an asymmetric molecule. Are there other chiral centers, chirality other than center of chirality and axis of chirality? Yes, of course, there is a axis of chirality and plane of chirality. Molecular axis is a chiral axis of the system. Molecule possessing a chiral plane is also a chiral nature. Finally, helicity, chirality is because of the twist in the molecule. Let us take axis of chirality. This molecule, is it chiral? Mirror image is written here. It has a plane of symmetry passing through the two chlorine atoms this way, bisecting the central bond. No, sorry, that's not a plane of symmetry. This molecule has a plane of symmetry. This has a plane of symmetry, it's clear, right? Yes. This also has a plane of symmetry, or a center of symmetry, for example, is there in this molecule. So as a result of that, this is not chiral in nature, it is not optically inactive molecules. Optically? This molecule has a center of symmetry. This is a center of symmetry. What is center of symmetry? It's a point from which you draw a line to a distance, let us say up to you meet C. Then go in the opposite direction, you will come with the same identical object. That is center of symmetry. Center of symmetry is there in this molecule, and that is why it is achiral in nature. It will be optically inactive in nature. It can have an axis. It cannot have a plane or a center. It can have an axis of symmetry, but not a plane of center. So, simple ethylene and cis trans isomers do not exhibit chirality because of the fact that they are symmetric in nature. On the other hand, if you consider allene as a molecule, allene is a conjugated molecule where the conjugation is on a single carbon. Here, what is the geometry of this molecule? This molecule has a plane which consists of these four elements, right? It also has another plane consisting of these four elements, but the plane is perpendicular to the original plane because of the way the pi orbitals are oriented. That is represented by the red line. The red portion of the plane is one plane and the colorless portion is another plane. And these two planes are perpendicular to each other. Are you able to visualize the molecule? So if I look at the molecule from this direction, along the axis, if I look at the molecule, what will I see? Let us take this here. I am viewing this molecule from this side. I am looking at the molecule from this side. You will have a horizontal bond first with hydrogen and chlorine. As you travel here, you will reach the end point here. The carbons are, of course, eclipsed on each other, top of each other. Then you will have the chlorine, hydrogen in this manner. That is how the molecule is going to look like. You are not going to see the central carbon because it is going to be eclipsed through the front carbon and the backside carbon. Are you able to see how it is drawn? This molecule is chiral. It has a C2 axis of symmetry, nevertheless it is chiral in nature. Why is it chiral in nature? Let me draw the structure again. What will happen if we try to lift this up and try to superimpose on top of the other? Can you superimpose it? You can superimpose the two hydrogen atoms and the carbon, but not the chlorines. Or one of the element is not going to be superimposed on top of each other. Are you able to visualize this? Can I proceed further? Let us say, for example, I want to bring this over here. If you try to superimpose the two chlorines and the hydrogen over here, these two chlorines will not superimpose on top of each other because of the twist of the molecule. You are not convinced. Let me try to explain it in a different way. If you want to superimpose these two hydrogen and chlorine on these two hydrogen and the chlorine, for example, I lift this up and put it on top of this. Okay? And the chlorine, hydrogen and this carbon will superimpose on top of each other. When I twist it like this, these two will interchange. Because these are in a different plane altogether. That is why. These are examples of molecules with a chiral axis. And the isomerism is called the atrope isomerism. Atrope means unable to rotate. Here this is a spirocyclic compound. Spirocyclic compound means a cyclic compound having a carbon which is common to both the rings. This carbon is common to both the rings, so it is a spirocyclic compound. The axis of symmetry is passing through the carbon here, and carbon here. That is axis of symmetry for this molecule. This is a biphenyl molecule, an aromatic compound with X and Y group attached to each other. Let's say X group is nitro group and the Y group is carboxylic acid group. This will not have a free rotation along the carbon-carbon axis because of the steric bulkiness of the nitro group and the COOH group here. So the complete rotation will not be possible. So that makes this a chiral molecule, because once it comes up to this certain distance, it will go back. So it will not rotate completely. So it has an axis of rotation. The axis of chirality is this axis is a chiral axis. Similarly, this axis is a chiral axis. This is a phosphine ligand. And nature, vancomycin is an antibiotic which has plenty of this kind of biphenyl derivatives, for example. This biphenyl derivative is essentially same as this one here. Here is a heterocyclic system with the indenyl derivative. This is this is a connectivity which makes the chiral axis in this particular case. Plane of chirality is again what do you understand from the structure where it is written? Now, this is a stacked system. This benzene is just on top of the other benzene ring. So the two benzene rings are on top of each other like this. This is called a 2,2 paracyclophane. Suppose I introduce a group here, bromine. That makes that molecule a chiral molecule. I put the bromine not on the ring. If I look at it from the top here, I will see 1, 2, 3. So that is a plane of chirality is there in the molecule. Here it has center of chirality. Here it is a plane of chirality. Yeah. Forget about the rest of the structure. Okay. Now I look at the molecule from the top. Do you see a handedness in the attachment of bromine? That is why it is chiral. And this is confined to the plane, so it is plane of chirality. As compared to this one, if you compare this, if you look at it this way, this is 1, 2, 3 anti-clockwise direction. This is 1, 2, 3 clockwise direction. That is why they are mirror images of each other. You can see that. This is not possible in the case of simple benzene, but in bridged benzenes it is possible. Simple benzene doesn't have plane of chirality because it is a planar molecule. This is a non-planar molecule. That is why the chirality comes into picture. Is it clear, the plane of chirality? This is an organometallic compound, again having two substituents, chlorine and methyl group. This is also a planar chiral molecule. You cannot superimpose this on top of this. If we try to superimpose on top of this, you can superimpose the rest of the structure, but the chlorine and methyl will be not superimposable. Helical structures are the most interesting chiral systems. You have the helix, which is alpha helix or the beta helix, right-handed helix and the left-handed helix are there. And these are some of the synthetic molecules which crystal structure is shown here. Here what is happening is you fuse the benzene ring like this. The benzene ring is a planar benzene ring. By the time it comes to fifth benzene ring, it has interaction with the other benzene ring on the other side. So they cannot occupy the same space. They will sort of twist and come up and down. That is the helicity that is formed. Helicity is formed only when you have more than 6 benzene rings in the system. 5 benzene rings you can still accommodate somehow. 6th benzene ring cannot be accommodated, so it goes out of plane, forming a helical structure like this. Okay. DNA molecule is the most celebrated helical molecule, and that is chiral in nature. Proteins have a lot of chirality. Amino acids are chiral, so the entire protein is chiral molecule. In addition to that, the secondary structures form the beta sheet and the alpha helix structures, which are chiral in nature. Alpha helix structures are chiral in nature. The tertiary structures are also chiral in nature. Here is an example of a hemoglobin protein. Alpha helix is a right-handed helix in this structure. Left-handed helix is not at all formed in the nature. Conclusion: symmetry is beautiful. Chirality is even more beautiful because it allows you to develop concepts and real-life situation molecules. Chirality, nature is plentiful. Molecular chirality is simply awesome. I will stop with this.